Alice needs to prove to Bob she knows a secret number. She can't tell him the number, she can't even talk to him. And Bob is actually thousands of Bitcoin nodes, including ones that don't exist yet. The solution, invented by Claus Schnorr in 1989, became the most compact signature in Bitcoin and the foundation of Taproot. Start with the building block. On an elliptic curve, multiplying a secret scalar x by a generator point g gives you a public key xg. Recovering x from xg is the discrete logarithm problem, computationally infeasible. So you can publish xg safely, but possession is harder. Anyone can copy xg. Alice needs to prove she actually knows the x behind it, without ever revealing x. That's a zero-knowledge proof, convincing someone of a fact while leaking nothing else. Schnorr's identity protocol works in 4 steps. Step 1. Alice picks a random nonce k, a single-use secret scalar, and sends the commitment kg to Bob. Step 2. Bob picks a random challenge e and sends it back. Step 3. Alice computes the response s equals k plus e times x and sends s to Bob. Step 4. Bob verifies that sg equals kg plus e times xg. Why does this work? Take Alice's equation, s equals k plus e times x, and then multiply both sides by g. You get sg equals kg plus e times xg, which is exactly what Bob checks. The verification passes only if Alice truly knew x. But Bob learns nothing about x because the nonce k masks it. That nonce is doing 2 jobs at once. It acts as a second unknown that prevents Bob from solving the equation for x, and it binds Alice's commitment before she ever sees the challenge. The order of these messages is not cosmetic. It is load-bearing. Imagine reversing it. Bob sends the challenge E first, then Alice commits. An attacker who does not know X can now forge a proof trivially. Watch carefully. The attacker picks any response S they like, say S equals 7, they take the challenge E, say 3, and the victim's public key xg. They compute kg equals sg minus e times xg. Then they output the pair kg, s, plug it into the verifier, sg equals kg plus e times xg by construction. It verifies perfectly. No knowledge of x required. This is exactly why Alice must commit to kg before seeing e. The commitment locks her into a specific k, so she cannot tailor her response to the challenge. This subtlety, commit first, challenge second, response third, is the heart of every Sigma protocol, and it is exactly what Fiat-Shamir must preserve. This works if Alice and Bob can talk, but Bitcoin has thousands of verifiers, including future ones. Interactive protocols don't scale. Enter the Fiat-Shamir transform. The insight is simple. Replace Bob's random challenge with a hash. Alice computes E equals h of kg herself. Using a cryptographic hash function like SHA-256, the hash output is unpredictable, so Alice can't choose it, which preserves the commit before challenge ordering. But it's reproducible, so any verifier, anywhere, anytime, can recompute the same E. We model the hash as a random oracle, an idealized function that returns uniform random output for every input. Now add the message. Set E equals h of kg concatenated with m, where m is the transaction being signed. The signature now binds to that exact message. Change 1 byte of m and the verification fails. We're not done yet. BIP340 adds one more input to the hash, the public key, capital XG itself. The final form of the challenge is E equals h of kg, capital XGM. So why include capital XG inside the hash? To see why, consider Bitcoin's BIP32 unhardened key derivation. A parent public key capital XG produces a child key equal to capital XG plus TG, where the offset T is publicly derivable by anyone. Now suppose Alice signs a message under the parent key, producing the signature KGS with challenge E equals h of KGM with no public key in the hash. Watch the attack unfold. The attacker computes a forged response S prime equal to S plus E times T. Then S prime times G equals SG plus E times TG, which expands to KG plus E times capital XG plus E times TG. Factoring, that's KG plus E times the quantity capital XG plus TG, which is exactly KG plus E times the child key. The forged signature KG S prime verifies under the child key, and the attacker never had to know the child's secret. A free forgery. Putting capital XG inside the hash breaks this attack cleanly. The challenge for the parent uses capital XG, while the challenge for the child uses capital XG plus TG. These are now different hash values. E parent is not equal to E child, and the algebraic shift no longer lines up. The forgery dies. We now have every piece. Let's assemble BIP340. To sign a message M with private key X, first pick a fresh nonce K, compute the commitment K times G, compute the challenge E equals the hash of KG, XG, and M. Compute the response S equals K plus E times X, and output the signature, the pair KG and S. To verify, given XG, the message M, and the signature, recompute E from the same hash, then check that S times G equals KG plus E times XG. Let's walk through tiny numbers to feel it. Let X equal 5, K equals 7, and suppose the hash gives E equals 3. Then S equals 7 plus 3 times 5, which is 22. For verification, 22G equals 7G plus 3 times 5G. Both sides equal 22G. It checks out. The math is clean because Schnorr is linear in the secret, and that linearity isn't just elegant, it's the property that unlocks everything else. Serialization is just as elegant. The signature is 2 scalars worth of data. Bytes 0 through 31 hold the x-coordinate of KG, 32 bytes, with the y-coordinate implicit because BIP340 fixes it to be even. Bytes 32 through 63 hold the response S, another 32 bytes. Total, exactly 64 bytes. One optional byte, 65 total, only if a non-default Cygash flag is used. That's the field telling Bitcoin which parts of the transaction this signature covers. One warning before we close. The nonce K is not just randomness, it's security critical. If K is predictable or worse, reused across 2 signatures with different messages, anyone can subtract the 2 equations and solve directly for X. Real wallets have been emptied this way. BIP340 specifies deterministic nonce generation, using a hash of the private key and the message, eliminating the entropy failure mode entirely. And remember, the inputs to the challenge hash aren't arbitrary either. KG enables Fiat-Shamir, M binds the message, XG blocks key shift forgeries. Each input has a job. 3 payoffs make Schnorr worth the migration. Provable security under discrete log plus the random oracle model. ECDSR has no such proof. Linearity, which enables music key aggregation, Frost threshold signatures, and adapter signatures. And a batch verification, checking many signatures together, is roughly twice as fast per block. 64 bytes, one academic paper from 1989, and the mathematical foundation that made Taproot possible.